Here's a more complicated function made up of f equals t, that's on this interval, and then at the transition point of 1, what we're going to get is the quadratic t squared afterwards. And so that function's fairly straightforward to write in piecewise form. It's the function t when 0 is less than or equal to t is less than or equal to 1, and then it transitions to t squared when t is larger than 1. And where you put the equal sign, it literally doesn't matter here because you get the same value either way. It has no impact on the final answer no matter what the function was, though, because integrals are all about areas, and the area at one point is always 0 anyway. So don't fuss too much about the less than or equal to versus strictly less than signs. Having written the piecewise form, we can't transform this. The Laplace of this is equal to what? I don't know. What we need to do is use our step function to rewrite this in a way that we can find the transform. So we're going to write that with our u function. Now the way we can do this is the function starts at time 0 with t. So we have t. And one of the ways to think of this u function is an on and off function. So we could say that t is being turned on at u0. Or at time 0. Now, how can we turn it off? What if we want to stop that t value at time 1? If you work it through, if we subtract u1 from this, what's going to happen? Well, when t is larger than 1, this step function is on, and also when t is larger than 1, this t is on at t equals 1. These are both going to be on, so we're going to get t times 1 minus 1, well that's t times 0. So this construction of one step function minus another is an excellent way to capture this interval notation. I want t, I want to turn on at 0, and then by subtracting another step function I'm going to have it turn off at this later time value. The second function in some ways is easier because we can simply add t squared, which turns on at 1, and then that is going to be something that never turns off again. It goes on forever, so we just have to turn it on, and we don't need this turning off syntax. Given that the step function is something many of you will not have seen before, it's worth thinking this through, maybe plotting some points, but at the end of the day, you'll find that this construction is a very simple way to translate from piecewise functions into notation that we can use with Laplace transforms. Here we've copied out that function again, and we're now asking what the Laplace transform of that is. Well, the first step is to look at each of these separately. So let's call the Laplace transform of t times u0 minus the Laplace transform of t times u1 plus the Laplace transform of t squared times u1. Now, we apply the rule that says if we transform a u, a times an f, we get an e to the minus as, and then we multiply it by, we're not done, by the transform of f of t plus whatever that a value was, whatever that on time was. That gives us here e to the negative 0s times the Laplace transform of t plus 0. Now that seems a little trivial, and it actually is. Keep in mind that the Laplace transform is an integral. It starts at 0, so whether things turn on at 0 or were off before doesn't really play a role, and we see that coming in the math here. Next term, we're going to subtract u1 times t and its transform. Here we get something a little more interesting. We get e to the negative 1s times the Laplace transform of t, but we want t plus 1 to make this work out. And last but not least, we're going to have e to the negative 1s for this term. The u1 gives us an e to the negative s times the Laplace of every t replaced by t plus whenever the switch was turned on, which is t plus 1 here. Now some of these first two terms in particular, we can just evaluate. This is just 1, that stays. The Laplace transform of t is in the table, it's 1 over s squared. Then we're going to subtract e to the negative s times the Laplace transform of t plus 1. And this one will have a transform of two terms, 1 over s squared for the t, 1 over s for the 1. Now this last term is a little more ugly. We have this t plus 1 squared. We really need to expand this. Again, the Laplace transform is linear, so it works great if we have a sum of things. It does not work so great if we have powers. So what we're going to do is expand that out and take the Laplace transform of t squared plus 2t plus 1. And then we get 1 over s squared e to the minus s, 1 over s squared plus 1 over s, another e to the negative s, and then we have t squared, 1 over s cubed, careful, 2 over s cubed, 2 factorial, plus 2, the transform of t is 1 over s squared, and last but not least, the transform of 1 is 1 over s. And that's the full transform. We could go one final step if we wanted and clean this up a little bit more. And it's usually a good idea to do that if you have the opportunity. Two of these terms have the same e to the negative x in common. And they also have some other terms in common. This is negative out front, so we have a negative 1 over s. That cancels with that. We also have a negative 1 and a plus 2. So at the end of the day, we have a 2 over s cubed plus a 1 over s squared. That transform is what we get when we have this piecewise function made up of a linear, then a quadratic, that breaks at the point time 1. And we can actually see that time 1 highlighted, once we get some practice, in the Laplace transform indicated by this e to the negative 1 times s.